Thank you for introduction. My name is Ren Taguchi, and today I'll talk about our study, concrete character analysis of binary curves by relation chain. Okay, sorry, this is the title. Okay, this is the abstract of today's talk. We improve FDT-based inversion algorithms for solving binary CDRP. In particular, we analyze the process of previous FDT-based inversion algorithms from the viewpoint of relation chains. More precisely, we propose two quantum FDT-based inversion algorithms. First, we propose our basic algorithm, which is based on pseudo FDT-based inversion algorithm. And also we propose extended algorithm, which is based on Manigasetti FDT-based inversion algorithms from CHES 2021. Finally, we compare quantum resources between our two algorithms and previous algorithms. The first, I talk about the background quantum tag to public cryptography. So as you know, RSA and replicate crypt are most widely used public key cryptography, and they are based on factoring problem and ECDRP. However, those problems are broken in Fourier time by Shor's quantum algorithm. But Shor's algorithm is currently not efficient in practice, since there are no sufficient large and accurate quantum computers. For example, the largest target of the largest target of factoring was only 21, and there is no experimental results for solving ECDRP. So we want a more efficient implementation of Schwartz algorithm. Now I will explain ECDRP briefly. I remark that rational points on an elliptic curve forms a group by point addition. Let P denote a rational point on an elliptic curve, and K denote natural integer, and Kp is the sum of Kp's. First, we consider the problem that computes Kp from P and K. This is a very easy problem. However, computing K from P and Kp is very difficult. This is a very curve discrete version problem called ECDRP. The ECDRP can be defined over arbitrary elliptic curves. However, several specific elliptic curves are used for cryptography. There are 3 elliptic curves for elliptic curve crypt recommended by NIST. Our study focuses on binary elliptic curves, and a binary elliptic curves of degree n is formulated by this, and these degrees are recommended by NIST. So now I describe point addition on a binary elliptic curve. Let P and Q denote rational points on the binary elliptic curve. Then P plus Q is given by this formulation, where lambda is calculated by this. Then, to calculate lambda, we compute an inversion on the binary field of degree n. To conclude, point addition on the binary field curves require an inversion on binary field. However, point addition is a part of Schwartz algorithm, and it is more expensive than another part, quantum Fourier transform. Therefore, to implement Schwartz algorithm more efficiently, we need an efficient quantum inversion algorithm on the binary field. So there are several works for efficient quantum based inversion algorithms, and they are concerned these quantum resources, Toffoli gates, qubits, CNOT gates, and depths. There are trade-offs between them. Then, sorry. although, previous works reduces the Toffoli gates and the qubits especially. And in particular, there are two major quantum wave inversion algorithms on binary curves: quantum GCD-based inversion and quantum FRT-based inversion. Quantum GCD-based inversion was proposed by Vanegas et al., and it achieves fewer qubits and fewer CNOT gates compared to quantum FRT-based inversion. We call this BBHL GCD. Then, quantum FRT-based inversion was proposed by Petrangelo et al. And Vanegas et al., and it achieves fewer Toffoli gates and fewer depths. We call these PWK-FRT and BBHL-FRT in each. In particular, PWK-FRT achieves fewer depths and fewer CNOT gates compared to BBHL-FRT, and BBHL-FRT achieves fewer qubits compared to PWK-FRT. Now, our study focuses on quantum FRT-based inversion. Here is the main results. First, we point out the fact that process of FRT-based inversion algorithm is based on specific addition chain. However, we show that we can construct a quantum FRT-based inversion algorithm whose process is based on arbitrary addition chain. In particular, we propose two quantum FRT-based inversion algorithms based on this fact: basic algorithm based on PWK-FRT, and extended algorithm based on BBHL-FRT. Next, we compare the quantum resources between our two algorithms and previous algorithms on discrete linearity curves. First, our basic algorithm reduces the number of qubits and CNOT gates for all n compared to PWK-FRT. For example, n equals 571, the number of qubits is 74% of PWK-FRTs, and the number of CNOT gate is 94% of PWK-FRT. Then, our extended algorithm also reduces the number of CNOT gates and depths for all n compared to BBHL-FRT. In case of n equals 571, the number of CNOT gates is 80% of BBHL-FRT, and the depth is 82% of BBHL-FRT. And here are the contents of today's talk. We explain the procedure of FRT-based inversion and its simple quantum implementation, PWK-FRT, using an example in case of n equals 163. Then, we introduce our basic algorithm, which is based on PWK-FRT. After that, we shortly describe BBHL-FRT and our extended algorithm. Finally, we compare our two algorithms and previous three inversion algorithms by measure quantum resources. So let's start explain the FRT-based inversion. So given F in the binary field of degree 163, we compute F inverse. We compute this by this relation by generalization of Fermat-Little theorem. Then F inverse equals square of F to the 2 to the 162 minus 1. Here though, please take care the only exponent part of 2. Then we compute this term by following steps, taking care of this relation 162 equal 2 to the 7 plus 2 to the 5 plus 2 to the 1. At the step 1, we compute these terms in this order, and at the step 2, we compute these terms in this order. Now I'll explain these steps in detail in next page. Okay, first, I note that F is written like this, 2 to 0, and our purpose is getting 162. At the step 1, we compute like this relation. In left side, 2 to the I minus 1 only appeared, and expanding this, the 2 to the I minus 1 is cancelled by multiplication, and we get 2 to the I. Let I equal 1, we get 2 to the 1 from only 2 to the 0, that is equal to input f. We repeat by I equals 7. And at the step 2, we compute like these relations. Expanding this, and 2 to the 5 is cancelled, and we get this. To conclude, we get 2 to the 7 plus 2 to the 5 only from 2 to the 7 and 2 to the 5. And then we get 2 to the 7 plus 2 to the 5 plus 2 to the 1, that is equal to 162 from 2 to the 7 plus 2 to the 5 and 2 to the 1. Then PWQ-FLT and BBHL-FLTs are quantum versions of this. So before I describe the quantum FLT-based inversion, I explained the quantum computation on the binary field. And this rectangle is a register and consists of 163 qubits. First, addition needs one register, and it stores 0 plus alpha equal alpha. And the squaring does not need a register, and alpha is replaced to squared alpha. Then multiplication needs a register, and it stores 0 plus alpha beta equal alpha beta. To conclude, addition and multiplication require a new register, that is clear qubits. Moreover, multiplication requires Toffoli gates. These three quantum computations also require CNOT gates. However, qubits and Toffoli gates are expected to be much more expensive than CNOT gates. So, we want to design quantum FLT-based inversion algorithms with fewer multiplication and fewer additions. So now I will explain the FLT-based inversion algorithm. First, we apply addition to get another 2 to the I minus 1, and we apply square repeatedly and get this, and apply multiplication, and we get 2 to the I. Then we require these two registers and one multiplication. And at step 2, we apply square repeatedly to 2 to the 7 and get this, and apply multiplication, we get this. Then we need this register and one multiplication. In total, we require 16 new registers and 9 multiplications. Then I explained the quantum resources for PWQ-FLT in general N. So let T denote the Hamming weight of n-1 in binary. Then there exist non-negative integers k1 to kt, which satisfies this inequality and this relation. And I know that k1 equals 4 of log n-1, that is bit ranks. That is the bit ranks of n-1 minus 1. Then we compute this term by following steps. At the step 1, we compute these in this order, and step 2, we compute these in this order. And the last term is 2 to the n minus 1 by this relation. In total, we require 2 times 4 of log n minus 1 plus t minus 1 new registers and 4 of log n minus 1 plus t minus 1 multiplications. Then we look back the procedure of PWQ-FLT. Now we point out to the orange board and pick up them. Then we get this sequence. So we find that this sequence is an addition chain for 162. So addition chain is defined by this, and simply saying for S there exists I and J which satisfies PS equal PI plus PJ. So we call PS a double term when I equals J, and an other term when I not equal J. For example, 2 is a double term because 2 equals 1 plus 1. And 2 to the 7 plus 2 to the 5 is the other term because we can get this by adding 2 to the 7 and 2 to the 5. So you may question that we can use an arbitrary addition chain for n minus 1. In other words, does there exist a quantum-based inversion algorithm that procedure is based on arbitrary chain for n minus 1? In fact, the answer is yes, and this is the main idea of our basic algorithm. So now I'll explain our basic algorithm in case of n equal 163. So we check the addition chain used in PWQ-FLT again, and we call this PS children. You see that PS children consists of 7 double terms and 2 other terms. And they correspond to a term calculated in step 1 and calculated in step 2 in each. I note that step 1 requires 2 new registers and one multiplication, and step 2 requires 1 register and 1 multiplication. In total, 16 new registers and 9 multiplications are required. However, our basic algorithm uses this addition chain, for example. This chain includes 5 double terms and 4 other terms, and they are calculated in step 1 and step 2 in each. Then, in total, we require 14 new registers and 9 multiplications. It is remarkable that our addition chain is the same length to PS children, but it has fewer double terms compared to PS children. So now I talk about the general case of basic algorithm. So we use an addition chain for n minus 1 of length L to calculate this. And PS consists of D double terms and M other terms. Here, our basic algorithm calculates these in this order, starting from this, using 2D plus M equal L plus D new registers and L multiplications. Then we analyze the addition chain used in PWQ-FLT, PS children. So we find L equal floor log n minus 1 plus t minus 1, and D equal floor of log n minus 1. PS children is easy to understand. However, it is not always the shortest addition chain for n minus 1. Therefore, we expect to find shorter addition chain for n minus 1 than PS children. Moreover, PS children has many double terms because of its way to construction. Therefore, we expect to find addition chains with fewer double terms than PS children. To conclude, it is desired that we find addition chains with fewer ranks L and fewer double terms D than PS children. However, if there are no shorter addition chains than PS children, we can reduce registers by finding addition chains with fewer D. Now, I'll talk about the BBH-FLT. The difference of BBH-FLT and PWK-FLT is only step 1. Now, I described PWK-FLT again. So we apply addition and apply square repeatedly and apply multiplication. And these 2 new registers and 1 multiplications are required. However, BBHFLT also get 2 to the I in the same way to PWKFLT. After that, we apply square inverse to this register and get 2 to the I minus 1 again, and apply addition, and we get initialized register. Then, we require one new register and one multiplication. Like this, we can reduce registers, but we need more CNOT gates and depths for addition and square inverse. So to conclude, BBHFLT is almost same to PWKFLT, but it reduces registers for cropping in step 1, sacrificing CNOT gates and depths. So we can also use arbitrary addition chain for n-1, and this is our extended algorithm. Our extended algorithm requires D plus M equal L new registers and L multiplications. So now we compare the content resources of our proposed algorithm, basic algorithm, and extended algorithm, and prior works. First, I explained our choice of addition chain for n-1. We chose addition chain having double terms as few as possible from shortest addition chains. In other words, we collect shortest addition chains of for n-1 first and pick up the chain, the fewer double terms. And here is a setting for comparison, and degree n's are all of least recommended. And we compared the number of Toffoli gate, qubits, CNOT gate, and depths in the whole Shor's algorithm. Then here are the L and D's of our addition chains and the comparison of quantum resources. In above 3 cases, we find the addition chain with fewer D, but the same ranks to PS children. Then, our basic algorithm achieves fewer qubits and fewer CNOT gates compared to PWKFLT, and extended algorithm achieves fewer CNOT gates and depths compared to BBHFLT. And in case of n equal 409 and 571, we find an addition chain with fewer ranks L and fewer D. Then, our basic algorithm reduces all quantum resources compared to PWKFLT, and extended algorithm also reduces all quantum resources compared to BBHFLT. Here is the detailed quantum resources in case of n equal 163. Then this is the case of n equal 571. Okay, this is the conclusion of today's presentation. Thank you for listening.
Thank you, Ran. Is there any questions from the audience? We have a little bit of time.
Okay. I believe that your analysis, which is very nice, ignores a particular topic. And this is that if you look at different addition chains, in some of them you are using only recently produced values, while in others you are using very old results which had been computed long ago, stored, and then used again later on. Assuming that you don't have perfect quantum computers, and therefore there is some decoherence which is happening, so very old registers might be less reliable compared to new ones. So when I compare different addition chains, I might prefer someone where I only use recently produced values and not very old values which had been stored for a long time. So you may want to look at this issue in addition to just how many steps you do in your addition chains. It's an element which you didn't take into account and could have a big effect in real quantum computing.
Thank you.
All right, so to respect the next speaker time, if there's any more questions, please save them till after this session. Thank you, Ren. I'll introduce our another round of applause for Ren. All right, the second speaker for this quantum cryptanalysis session is going to be Jiayu Zhu. He is the assistant professor for Oregon State University. Thank you.
Okay, great. Sorry. Okay, so good morning, and thank you for the introduction. So today I'm going to talk about classical and quantum security of elliptic curve VRF, or ECVRF, via so-called relative indifferentiability. So this is joint work with Chris Pikert, who is at both University of Michigan and Algorand. I will skip this. And so here's an outline of my talk. So first of all, I will talk about the background, like what is VRF, what is ECVRF, and what's the prior work done in this field. And then I will talk about our two main contributions. One is we introduce a new security notion for ECVRF called non-malleability, and the second is we analyzed this so-called full uniqueness of ECVRF in both the classical setting and the quantum setting. And then I will briefly conclude. So ECVRF is a specific scheme of verifiable random function, or VRF. So this is a very old cryptographic primitive first introduced by Micali, Rabin, and Vatman in 1999. So you can view it as a public key version of pseudo-random functions, or PRFs. So there are two people here. One is the so-called prover, and the other is the so-called evaluator, or verifier. So the prover generates a pair of secret key and public key, and of course broadcasts the public key. So the verifier only knows the public key. And then the verifier sends a function input, let's call it x. And then this prover evaluates the function output of x, called y, using the secret key. And also, together with this output y, the prover also sends so-called proof pi, again using the secret key. And then the prover sends to the verifier both the function output y and the proof pi. And the verifier, using this y pi and, of course, the public key, can verify whether this y was computed correctly. So if computed correctly, then the verifier can output 1 or accept. Otherwise, the verifier rejects. So this is the basic definition of a VRF. Of course, this evaluation procedure can be done again and again. So traditionally, there are three properties for VRFs. The first one is, of course, completeness or correctness. So basically, it says if the proof is indeed generated correctly, then the verifier will output 1. The second is the so-called uniqueness. So this says for any input x, so it is infeasible to find a valid proof for two different outputs, y1 and y2. Of course, this implies that because y1 and y2 are different, so there are only one of them that can be correct. So this implies that it is infeasible to find a valid proof for an incorrectly generated function output. Of course, there are several variants of this uniqueness definition. So you can ask, what exactly does it mean to say infeasible to find? So is it perfect, which means that the probability of anyone finding such two valid proofs is 0, or is it statistical? Is it computational? And also, can the adversary choose the public key, or is the public key honestly generated and given to the adversary? So there are a lot of variants. And finally, the second traditional property is so-called pseudo-randomness. So this is if the verifier is adversarial. In other words, for an adversary that only knows the public key but doesn't know the secret key, then the function values should appear random. So these are the three traditional security properties for VRFs. And there have been a lot of applications of VRFs. So I listed some of them in zero-knowledge proofs, in lottery system, in electronic cash, and very recently, it has been very widely deployed in blockchain and cryptocurrency systems. So one specific scheme for VRF called elliptic curve VRF, or EC-VRF. So this is a relatively new development. This was first proposed in 2017. And there's an internet draft for this scheme, and it has evolved a lot. So currently, it is, last time I checked, it is in the 15th version. So the significance of this EC-VRF is it is currently under consideration for standardization by CFRG, by Crypto Forum Research Group. And so this is the ongoing process, and it has not been standardized. But even now, it has already been widely used in not one, but several cryptocurrency systems. So it is something that is actually being used in practice. So while proposing this EC-VRF, of course, that paper provided security analysis. So completeness or correctness is perfect, and this is very straightforward. You can directly see it from the description of the scheme. Uniqueness, computational uniqueness, is proved in the random oracle model against a classical, which means non-quantum attackers. And pseudo-randomness is also proved in the random oracle model, only against classical adversaries, and this is proved under the decisional Diffie-Hellman assumption for the elliptic curve group. So we noticed that in that prior EC-VRF analysis, there are several, call it gaps, or call it something that is not very complete. So the first thing is they only prove those three traditional security properties for EC-VRF. And because after their paper came out, this EC-VRF has been widely used in cryptocurrency systems. And in those scenarios, people realized that certain applications need some additional security properties that were not even introduced before. So this is the first thing. The second thing is there are some very minor at first glance, but very subtle differences between the paper version in 2007 and the internet draft version, which is currently under consideration for standardization. So this means that the security analysis of the paper version doesn't necessarily directly apply to the internet draft version, and nobody has really analyzed the internet draft version. So the first thing is, the third thing is, their security analysis only considers the classical setting. In other words, there's no post-quantum security analysis at all. Because the pseudo-randomness relies on DDH assumption for the group, which is trivially broken if there's a quantum attacker. So this means that a quantum attacker can easily break pseudo-randomness. But other properties, whether they are also broken when there's a quantum attacker, this is not very clear. And in particular, the prior uniqueness proof, that one is against computational adversaries. But it is computational in the sense that you need an upper bound of the adversary's number of random oracle queries. It doesn't really need any computational hardness assumptions. So it is possible that this uniqueness still holds against quantum adversaries. So here comes our contributions. So the first contribution is we analyze ECVRF exactly as in the internet draft version rather than the paper version. So we notice that there's some changes on which exact things are put into which exact hash function. And so this means that the prior proof techniques don't directly apply to the internet draft version for some very subtle technical reasons. So to prove those security properties for this internet draft version, we came up some new concepts and proofs, which is called relative indifferentiability. So this is a technical contribution. Our second contribution is for the cryptocurrencies setting, we proposed some new security notions and proofs for ECVRF, including what we call non-malleability, strong non-malleability, and binding. And finally, we noticed and proved that this uniqueness property still holds even if the adversary is quantum. So now I'm going to talk a little bit about this non-malleability of ECVRF. So the motivation is like this. So if you have a consensus protocol, say in the blockchain setting, so there are two people. So the first person transmits the VRF output together with the proof. Let's call this proof pi. And let's say there's a man in the middle adversary who can change the message sent between the two honest parties. So this adversary can replace this proof pi with some other proof pi star. And if this pi star is still valid, then the receiver will accept. And this means that the two blocks for the two different honest parties will be different. So there's actually no consensus reached. So to counter this type of attacks, so we propose the concept of non-malleability, which basically says, of course, if the attacker is given, let's say the attacker is given oracle access to the prover, to the proving algorithm, then of course the adversary can query again and again and generate some valid input-output proof tuples. But non-malleability says it is infeasible to generate any new valid such tuple. So this basically stops the attacks I showed in the previous slide. So here's a graphical illustration of what non-malleability says. So this adversary can query the proving algorithm on inputs x1 to xq, and of course the oracle gives the adversary y1 pi 1 to yq pi q. And non-malleability says the adversary cannot output a new input-output proof tuple where the proof is new. And strong non-malleability says the adversary cannot output a tuple of input-output proof where the tuple is new. So we proved that ECVRF is non-malleable in the random oracle model under the discrete logarithm assumption in the group. So ECVRF is, it can be viewed in multiple ways. So if you view it from one point of view, it is very similar to the Schnorr signature scheme. And our non-malleability proof exactly uses this rewinding technique, also called the forking lemma, which was first proposed while proving the security of Schnorr signature scheme. So just to very briefly recap, so the basic idea is you run the adversary twice, and you break discrete logarithm assumption if the adversary wins twice. So this means that you have a quadratic security loss because you need the adversary to win twice. So the very high-level idea of this non-malleability is roughly the same with the idea of proving Schnorr signature scheme secure. But there are some technical differences. And we also propose this new security notion called binding. So this is, it is infeasible to generate two different tuples of public key input and output. So there's no, and also just a single proof which is valid under both tuples. So here we prove that this ECVRF is full binding, assuming that the hash functions are collision resistant. So here we don't even rely on random oracle model, and we don't have any computational hardness assumptions. We only need the hash function to be collision resistant. And we also showed that non-malleability plus trusted binding, which is slightly weaker than full binding. So these two combined imply strong non-malleability. So in other words, if we work in the random oracle model and we assume discrete logarithm assumption, then we showed that ECVRF is strongly non-malleable. Is it possible to prove non-malleability against quantum adversaries? So as I think this is what Ren, the previous speaker, also talked about. So discrete logarithm is easily broken if there's a quantum attacker due to Shor's algorithm. So if there's a quantum attacker, then non-malleability is completely broken. There's no hope here. So our second main contribution is the full uniqueness of ECVRF. Again, this is an analysis of the internet draft version, not the paper version. And we also consider quantum adversaries. So full uniqueness, again, it says it is infeasible to produce public key input and two different outputs with two valid proofs. So here, the adversary is allowed to control the public key. So the paper version proved that the paper proved that the paper version of ECVRF is fully unique in the random oracle model against classical adversaries. So the idea here is this proof, essentially it is a non-interactive zero-knowledge proof for the equality of discrete logarithms. So there are three steps. So in the first step, you prove that the corresponding interactive proof is sound. And then in the second step, you do a Fiat-Shamir heuristic, and you prove that the corresponding non-interactive proof is sound in the random oracle model. And then in the third step, from there, you show that ECVRF satisfies uniqueness. So our basic observation is that the same approach also works for the quantum setting. But there's a minor difference between the paper version and the internet draft version. So basically, which exact thing is hashed in which exact hash function? So in the paper version, the public key is hashed. There's an inner hash and an outer hash. So in the paper version, the public key is hashed in the outer version, in the outer hash, and in the internet draft version, it is hashed in the inner hash. So there's this subtle difference. So fortunately, there's this concept called indifferentiability, which basically says, very roughly speaking, putting the input in the inner hash and putting the input in the outer hash, these two should be equally secure. This is a very, very high-level idea of what indifferentiability says. And this holds even in the quantum setting. So at this point, it seems that we are safe. So we can conclude that using indifferentiability, we can prove full uniqueness for ECVRF even in the quantum setting. There's a very subtle technical point, which is, I cannot get into the details, but the basic point is indifferentiability is basically saying comparing some real object with some ideal object. And it says real object is as secure as the ideal object. Here the problem is, if you just use the ideal object in ECVRF, then it is insecure. So the problem is the so-called simulator here is given too much power, including programming this random oracle. So for this reason, we need something stronger than indifferentiability. And we call it indifferentiability relative to some external oracle. And using our new concept, we indeed prove that this internet draft version of ECVRF is fully unique in both the random oracle model and the quantum random oracle model. So it is secure in both the classical sense and the quantum sense. So just to briefly recap, so 3 contributions. The first is we proposed some new security notions. The second thing is we proved the full uniqueness of ECVRF as in the internet draft version and not in the paper version. And this is against quantum adversaries. And finally, we have this technical contribution, a new concept called relative indifferentiability. And we believe that this has the potential application to some other contexts, other scenarios. So this is the end of my talk. Thank you.
I think we have time for one question before the end of the session.
Thanks for the talk, Jiayu. There were differences between the paper version and the draft version regarding what was hashed in which place. Do you know why those changes were made? Are there other security justifications?
So to be honest with you, I don't know the reason. And what I do know is, so this ECVRF, this scheme has a kind of a messy development. So the authors of ECVRF changed their scheme. I mean, every change is very minor and very subtle, but they changed their scheme a number of times. So after we found out that there's this discrepancy, this gap between the internet draft version and the paper version, and that gap leads to some difficulties for some security analysis. So we found this and we reported this to the those ECVRF authors. And these authors basically changed this ECVRF internet draft version back to their paper version. So this is due to our analysis. So if you look at our paper, so I think there's a footnote which says actually the current ECVRF internet draft version is back to the paper version, and this is due to our observation in our paper.
Alrighty, thank you everyone for joining. Thank you again to our speakers, Jiayu and Ren.
Yeah.